gas molecules travel in straight lines till they run into something and they bounce off. So the mean free path is the average distance that a molecule can be flying through, well, not the air, but through space, without hitting something. If you increase the pressure, the particles are going to be closer together or traveling faster, and so the mean free path is going to get smaller. And just to give you an idea for scale, if you're looking at nitrogen, and nitrogen was the size of a golf ball, it could travel about 40 feet before it runs into something, and then it's going to bounce off. That's on average. So we're going to talk about two things that gases do, diffusion and effusion. So diffusion is the process by which gas molecules spread out from a high concentration to a low concentration. And we've learned that smaller particles travel faster and heavier particles travel more slowly. So gases that have more mass are going to diffuse more slowly. Effusion is the process in which a gas escapes through a small hole into a vacuum. This is also dependent on the root mean square average velocity. So a lighter gas will effuse faster than a heavier gas. So we can tell that the rate of gas movement will be inversely proportional to the square root of its molar mass, which brings us to this equation known as Graham's Law of Effusion. So the rate at which A effuses compared to the rate at which B effuses is going to be equal to the square root of the molar mass of B over A, because a heavier particle effuses slower and a light particle effuses faster. So velocity is high when mass is low. And this is an illustration of gas effusing. So here we have a container with a gas in it, and originally this side had no gas in it, and there's a hole here. Now, what I think of when I see that is I think of, well, that's a vacuum. That's going to be sucking the gas out, right? No, actually not. These particles are just zinging around, completely oblivious to the fact that there's a vacuum on the other side of the wall. Occasionally, one of these will have a direct hit on that hole and go through. And then over here, it's going to be bouncing around over here. And gradually, more and more particles are going to happen through that hole. So it's not that they're being sucked out or pushed out. The hole happens to be in their path, and so then they go to the other side. That was just like, yeah, you think about that one for a while. So helium balloons will shrink up faster than balloons with air in them. And it's not because the particles are smaller, specifically, it's that they're faster. Because a latex balloon has little teeny tiny holes in it. That's how the air or the helium gets out. But it's not that the air particles don't fit through the holes. It's just that they're moving more slowly, and so they don't hit the holes as often to escape. Find the ratio of the fusion rate of hydrogen gas to that of krypton gas. These questions bother students a lot because, look, there's no numbers. But I have to use an equation and calculate a number, and I'm not given any numbers. This is somehow wrong, right? Okay, so we're going to use Graham's Law of Effusion, and we're looking at the ratio of hydrogen to krypton. So I forgot rate. So what I'm looking at here, I'm looking at the rate of hydrogen gas to the rate of krypton gas. That's the ratio of their rates. And that's going to be equal to the square root of the molar mass of krypton divided by the molar mass of hydrogen.
Is there a reason why you took it?
Yes, because this is how the equation is. So A on top here, A on the bottom there. Because a lower molar mass gives us a higher rate, because they move faster. Great question. So this is derived from the root mean square equation, which had the molar masses in kilograms per mole. But here, I'm going to take one of those and divide by the other, and so yes, I can convert them to kilograms per mole, but the conversions cancel out. So I can also do this in grams per mole, and I hope that doesn't bother anyone. So I'm looking for the molar mass of krypton, 83.80 grams per mole, and hydrogen would be 2.016 grams per mole. So the square root of 83.8 divided by 2.016. 6.447. So hydrogen will effuse, escape through that little hole, 6.447 times faster than krypton would. Now, why you would care about that is another question entirely. Any questions?